I'm going to take a lecture on the applications of GNSS in geodynamics study. So through this lecture, I will try to explain you how GNSS technology helpful in studying the geodynamics process, crystal deformations, and then how it is helpful in quantifying the deformation. So there are so many process going on the Earth surface, like landslides are there, earthquakes are there, land subsidence are there, then crack development, rock failure. So many deformations occurring on the surface of the Earth. So this is one of the technique. There are so many other technique also, but this is the one of the technique, potential technique, which is helpful in studying this geodynamic studies and quantifying the geodynamics process. So everybody know that this in the 20th century, before the era of GPS, our satellite navigation, we had this ground-based technique. It is also called triangulation method. So researchers were using the theodolite, and they tried to locate the different reference point. And once they get the 3 reference point, then they try to estimate the location. So we had this analog based. So these days we have digital based, but before this GPS era, we had analog based location measurement. So this tectonic geodesy can determine the position of geodetic monument and monitor how position changes over time. So as I told you, this is detecting the motion of geodetic movement with triangulation, and which measures the angle between the monuments using the theodolite, and this trilateration, which measures the distance with the laser. But presently, and then after that, we jump into very long baseline interferometry. This is before GPS. So we started with a very long baseline interferometry. Then what is the difference between this angle-based measurement and VLBI? It uses the difference between the time when the radio signals from the distant your celestial bodies arrives at different point on Earth. So this is the two difference. Then the third technique, we are using the satellite laser ranging. The satellite laser ranging uses the time required by time from the ground-based laser to bounce off from satellites. So this also gave a very enormous information about the navigation. But these methods are very costly affair actually. So you have to, and also this is not continuous. So that's why it becomes very difficult to use this method for deformation purpose. So then this global positioning came into the picture, where it is having very good time resolution, and it is also cost effective. You have to pay low budget and more output. Then you can have more network. But in case of SLR, VLBI, that's theodolite based. So it is time consuming, but also a very costly affair, and it is time resolution is also not good. So that's why this GNSS means GPS. In 20th century we had GPS, but now in 21st century we are telling it is GNSS. Why? Because we have so many navigation constellations these days, like GLONASS, Galileo, Beidou, Indian IIRS is there. Then China is also having Beidou, and Japan is having QZSS, quasi-zenith satellite system. We have navigation with Indian constellation. So like that. So some are your regional navigation system, and some of them running, having their global navigation system. So GPS is one of the very potential technique, and it is based on the travel time of measurement of the travel time of radio signals between the satellites and ground stations. This satellite based is cheaper, easier, faster, and doesn't require sight to be visible from each other. So line of sight is not required. But in the other method, we have to have line of sight. And then we can use in plate motion measurement, plate boundary deformation measurement, intraplate deformation. So intraplate means if something, if any deformation is happening on the plate itself, like Indian plate, so then we can do the measurement. Plate boundary, so if a deformation is occurring between two plates, then you can determine and quantify how much two plates are moving to each other. Then earthquake cycle, volcanic processes, land subsidence, etc. We can do these days with the help of GPS. So this is one of the ITR 2014 vectors. So you can see they are having different magnitude, different direction on different plates, on different plate boundary. So we can see over different countries. So we can see some of the plates showing less magnitude, and then some of the plates showing high magnitude. So it determines that your plates are moving with high rate, and these locations are moving with low rate. So and they are having different angle as well. So this whole vectors giving the idea about the geodynamics process, our plate tectonics of the earth, that how the different plate having their kinematics. So this is this we get once we have a continuous data at our site, means station. Then once we get the continuous data for 3 years, 4 years, 5 years, like that, then we process the data. So there are software to process the data. So this double differentiation, single differentiation we apply, and this all I hope it has been covered in your previous lecture by different faculty. So because this is not the part of my lecture, so I will directly jump into application part. So that's what once you get this data, so you process the data, then you get this magnitude and direction. So initially you get data per day data like latitude, longitude, and height. So you know this latitude mainly vary in north-south direction, longitude vary in east-west direction. So and then vertical is in vertical direction. So this latitude and longitude is with reference to your prime meridian and equator. So these are the reference plane. But in case of your this vertical, it is with respect to your ellipsoidal model of the Earth, and these all are estimated with respect to the center of the Earth. So that's why we, in another term, we say it is this all coordinate are with respect to the center of the Earth. So it is also called geocentric coordinate. So once you get this geocentric coordinate, then you get the mean of this, and then with the help of that you derive the displacement per day, how much displacement occurring at each site, and with the help of displacement you estimate the velocity, north-south direction velocity, and east-west direction and west velocity, and vertical direction velocity. So once you get this horizontal velocity, east-west and north-south is something horizontal velocity. So with the help of this velocity, we go for this result in motion. So these are result in motion actually. So you can see these are moving in south east direction, and our Indian plate is moving in northeast direction. So this arrow direction demarcating the direction of the movement of the plate. So this is moving in north-west direction. So, but here you can see the magnitude is very, very high. This Australian plate and this overing region, surrounding region showing the plate is having with high rate than the other location. So the strain accumulation and all are very, very, it's occurring with very high rate, because that's why we can expect this big size, big magnitude of earthquake in this region wherever there is a plate boundary. So plate boundary, and where there is a convergence plate boundary, so we can so an energy accumulation will take place over the region, and if it is releasing in a short recurrence interval, then we may expect lesser medium size earthquake. Otherwise, if it is a recurrence interval is very, very high, so we can expect bigger size earthquake. So this is how we differentiate the energy accumulation and release in the form of earthquake. So you know that this Galileo, QZSS, then GPS, compass, then INSS, GLONASS. This is the how it look like, and then this is the parameters of GNSS constellation. So you can see the GPS is having around 32 operational, GLONASS is having around 36 plus 2 in testing, then Beidou is having around 50, Galileo 24, Navic 7, then QZSS 4. Then you can see the orbit, medium Earth orbit, then in Beidou some are in medium orbit, then IGSO, inclined geosynchronous, then geostationary, one is geostationary, then Galileo is having medium orbit. So we can say that GPS, GLONASS and Galileo, these three are having similar infrastructure in the space, but Beidou is also beating these three, but they are having inclined geosynchronous as well as geostationary. But India is having only inclined geosynchronous and geostationary. So 4 is having inclined and 3 is having geostationary. So why this? Because they are orbiting at 36,000 kilometer altitude, and medium Earth orbit they are around 20,000, 22,000 like that. And QZ is also, so these two are regional, but these 4 are global. And these are the frequencies which they are transmitting continuously. So, and but here the uniqueness is in Navic. We have L5 and S band. So S band you don't see in any of the constellation. So it is only equipped with Navic. So it is having 2492 megahertz frequency, and the advantage of using this, it will perturb very less. Means this dispersion will take very less when it will travel or propagate through the ionosphere. So you can have very less error in this frequency when it is acquiring in our satellite. So still the testing is going on. Very soon it will be operational to the civilians, and we are also capturing L5, but still we are waiting to get, because these are restricted signal. So we are waiting to get this signal, and very soon we will get this both, and then we can go for millimeter level precision using this Navic constellation, as all the satellites are almost everywhere on the Indian territory. Then there are some augmentation system also. So we have Gagan, then European having EGNOS, like that. So this is the 24 hours visibility of the satellite. So you can see the maximum cluster is occurring, maximum cluster of the navigation satellite is occurring in this Asian region, and you can see that this is going around 50 plus, and this is after masking the 15 degree angle. So if the satellite is lower than this 15-degree elevation angle, so it has been masked. So you can see the advantage of using GNSS in navigation objective. So it is a very good number to get the very precise and good volume of data. So these are the error budget which associated with the data, and these are the processes and mechanism goes during the acquisition of this GNSS data. So we have to remove all these ambiguities like orbit error, clock error, then propagation related ionosphere, troposphere, then GPS related clock, multipath, antenna phase center variation. So and then this is related to the environmental, and then some this geophysical phenomena. So these all have to be removed, and then this is the formula which we ultimately use for each satellite and ground station pair. And once we create the pair, then we go for the partial equation derivation, and then we use the least square estimation also to remove the ionosphere error from the data, and then we get the final product. So this is the GPS signal. So presently we are more relying on this GPS data for this geodynamic study. Why? Because all the error budgets are very precisely available on the, and it is available time to time, and it is providing to the researcher. So because they have a very long period data, they have operations since 3 decades. So that's why they know all the error budget in atmosphere as well as on the ground, and they are monitoring 500 plus IGS station as well. And apart from this, they are having good volume of data of DORIS, SLR, VLBI, and other laser ranging. So these all are data very significantly helping to get the error budget and to remove all these ambiguities from our observation, and to get the millimeter accuracy, because this geodynamics study is dependent on millimeter accuracy. So if you don't have a millimeter accuracy, you cannot do this study. So this is the limitation of this study. So that's why we have to have very good and very less error data, so that when we are going for the processing, our human error should be very, very less, and whatever the error associated with the technology related. So already this GPS is providing the solving all this error, and then we are getting millimeter accuracy and precision as well. So this is the code signal, and this is carrier signal. So when this the rough estimate means when we are getting the latitude, longitude, a priori information of the site, we are using this code data. So very quickly we are getting this information through this code data. But when we are going for this high quality data processing, then we are using carrier wave. Because why carrier wave? Because it is like a Bernal calipers. So we have a very precise informations of the phase. So if there is any fraction of change occurring due to different phenomena, so it can be captured in the phase data as compared to the carrier data, because it is varying only in 0 and 1. But here you can see it is it is having amplitude as well as time. So and it is not constant. It is it is dependent on time and also the process and mechanism which is occurring. So if something is there, it can be captured in your carrier data. So these are the model to get your pseudo range, and this is the model to get the length using the phase data. So this is how this time delay occur in the pseudo range. So ultimately you have to rectify this time delay so that you should, this true range should be converted into true range. So actually we want true range. If there is no hindrance, if there is no error, then we can get true range, but we are not getting it. we are getting the pseudo range due to all these issues. So these are some errors. Then this is the mathematics, so which we use to derive the four unknowns. Four unknowns are your x, y, z, and time. So with the help of this, we model this equation, and as more as satellite are there, the more equations will form, and then you can have good this information about the error budget, and then we can get the millimeter accuracy. So these are the carrier phase models. This is the single difference sensing and double difference sensing to eliminate the clock error from the users and eliminate the clock error from the satellite. So these are the stations, permanent stations we are monitoring in Himalayan region and in Indo-Gangetic region. And these are the campaign stations. We are going episodically and acquiring the data, campaign data for 4 to 5 days, and then we are processing, and then we are going for this modeling purpose. So this is the study carried out in Indo-Gangetic plain and lesser Himalaya and higher Himalaya. So you can see that this is the ITRF 2008 velocity. So ITRF is nothing but it's a reference system. So it's a datum. So like you must have used this different datum system, like WGS84 is there. So it's very old, but it is getting modified time to time when we have very precise information about the geoid and ellipsoid of the Earth. Then it is getting modified, and then we are having a different generation of datum. So this is the 2008 and 2014. These are two different datum of two different generation. So this they are very reliable for this study, because with the help of this data we are estimating the different velocity, direction velocity, north-south velocity, east-west velocity, and then vertical. So vertical we are estimating with the help of ellipsoidal model of the Earth. So this is the resultant velocity. You can see this is Saharanpur, this is Roorkee, this is Haridwar, this is Mohan, this is Mussoorie, Rajpur. So all these are there. So you can see the resultant velocity. So is movement is in northeast directions, and this is the error. So you can see that. Then this is the velocity in the lesser part of lesser Himalaya and higher Himalaya. So when you go from south to north, your velocity decreases actually with respect to ITRF, International Terrestrial Reference Frame. So we can clearly see that this vector magnitude is less here. This is Malari. So this is almost China-India border. So then this is Pantanagar. So this gives the idea that here the moment is there is no problem. So this obstruction is less compared to here. So this obstruction is more here because due to this China plate and all. So this is not allowing the plate to move in freely. But here, due to this less obstruction, here the moment is resultant motion is less. So when we estimate, so this is the time series this displacement of campaign stations. So you can, as I told you, we go periodically to get the campaign data. So that's why we get 2 point, we get 3 point, 4 point, 5 point, like that. So here it is 3 time measurement, here it is 4 time measurement, and here it is 5 time measurement. So depending on the time and all, we go for this measurement. So you can see this is coming in 1 millimeter, 0.9 millimeter, 1.3 millimeter. So we can expect little bit more error in campaign data than permanent, because permanent is something, it is providing the continuous information, but campaign data is a episodic data, so it is not continuous. So that's why your error ambiguity cannot be resolved 100%. But in case of this GPS, we are resolving error component 95%, and only 5% we are uncertain that it is having some more error. But in case of this is also 95%, but due to this periodic data, some of this error it is still remain in the data, so that's why we are not able to resolve it. But you see the this error, it is coming less than 2, so less than 2 millimeter, it is perfect enough to go for this geodynamic study. So you can see this is north-south component. So this is your north-south component, this is east-west component. So like that we have used this 2-component measurement for this geodynamic study. Then this is your continuous data. So you can see there's some gap also. So some gaps determined is due to the technical issue at the site. So it might be due for power failure. It might be some your technical issue with the receiver, antenna. So anything could be there. Any problem could be this. So due to this, you may not get the 365 days data. So but you can see the continuity. So it is continuous. So it is going, and then it is giving very ample information about the site and about the surrounding area, that how this different error budget and all are working at this site. So this is your north component. So you see the error, it is 0.4 millimeter per year error is there. So this is 95% error ellipse. So it is to your 2 sigma error is there. So there is a 3 sigma, there is a 1 sigma, so like that. So this is east-west velocity. So this is for Pantnagar, which is nearby Haldwani, and this is Mandal station information. It is situated in Chamoli region. So we can see that this station is not the time series you see that it is not straight, it is not linear, it is having sinusoidal. Why sinusoidal? Because of the seasonal hydrological contribution. So that's why you are getting, this is not only having tectonic component, but this is having non-tectonic component also. So this information we get through this GNSS site. So and we expect this non-tectonic component means seasonal hydrological loading impact on the site more when on the station which are placed in the higher Himalaya. So here you can see it is not placed in the higher Himalaya, it is in the Indo-Gangetic plain. So that's why this reform seasonal contribution, non-tectonic contribution is less compared to your Chamoli station. And also you can see in the east-west component. So east-west component, this is almost linear. So and also this Mandal also. So because in east-west direction, this seasonal motion movement is less. So and you know that this Indian plate mainly this convergence and convergence is going in northeast direction. So that's why we can expect more this impact of this seasonal hydrological loading in the north component. Then this is the non-tectonic component. Non-tectonic component you can remove, so you can see that so it is coming sinusoidal motion in Pantnagar station as well as in Mandal station. So in Mandal station you can see very conspicuously this your sinusoidal motion is detected due to this hydrological loading, but it is less in east-west component as well as in this Pantnagar station as well. So Pantnagar station is also giving some this detected some capture non-hydrological loading, sorry, non-tectonic component. But if you compare with Mandal station, so it is very high in Mandal stations. So it is coming in short interval, but it is occurring in long interval, and then amplitude is also less compared to the amplitude of the Mandal station. Then these are some published literature by our Indian researcher as well as foreign researcher. So you can see the plate velocity. So this is your Chennai, Bangalore, Hyderabad, then your Maharashtra, then Gujarat, then your Himalayan region. So you can see starting from south to north, you can see this all the site showing northeast direction. So you can clearly see that of different magnitude. So here we get maximum magnitude. It is around 55 millimeter per year. But when you go toward north, it is decreasing actually, and so on an average we can say the movement of the Indian plate is 50 millimeter per year, means 5 centimeter per year. So this is the movement of the Indian plate. But when we move into the Himalaya, so when we are further going into deep, so then we can see that the velocity decreases and it goes to your 32, 33 millimeter per year in higher Himalaya like Badrinath, Kedarnath, Malari. So these locations depict that your movement is around 33 millimeter, 34 millimeter per year. So where the rest of this amount is going, where it is consuming, where it is absorbing. So it is the area of interest. So we can say that this it is converting in the form of crustal shortening, vertical upliftment is going on, and this strain accumulation is going on, which these are the things these are very potential to create a mega thrust earthquake in near futures. So depending on the recurrence interval and the accumulation of the strain energy, so and it will create mega thrust, our medium size of earthquake. So I will discuss the case study also. So we have carried out the case study in Garhwal region and Kumayu region. So like that. So if you compare this velocity, so in this region you get less velocity, and in northeast region you get more velocity. And why more velocity? Because our Indian plate is having anti-clockwise motion. So due to this anti-clockwise motion, you get more velocity here and less velocity here. And this strain accumulation is also vary, and the convergence rate is also vary from northwest to northeast. So this researchers Jade madam used this information and estimated the Euler pole of this Indian plate. So you can see the Euler pole. This is coming here. So as I told you, this is having anti-clockwise motion. So it should have some pole. With respect to that, it is moving into this motion. It is so where is that pole? So this the pole is estimated in this location, and this is estimated by other researcher. So this is UK. So this is UK, and then this is Europe. So in Jade et al. Has estimated that this Euler pole is coming in this location. Now this is the regional strain component. So this is principal maximum and maximum extension and minimum extension. So you can see the compression and extension. So these are the compression and extension. So here you can see the vector is little bit. So when the arrow goes inside, so we interpret that the compression is going on, and then where the arrow is going away from each other, and we can say the extension is going on. So extension means area is extended, or we can say that it is having normal fault. So then we can say the extension. Then compression means compression is going on. So maybe some thrust fault is there. So due to that, this compression is going on. So here also you can see the compression and extension. So some location can give compression and extension both of same magnitude, because this whole plate is moving due to this geodynamic process. So this convection current and all these are the driving force, which is giving the force to the Indian plate, and it is constantly moving in north direction. And then this is the velocity with respect to Indian plate. So we have fixed the Indian plate, and then this velocity has been estimated So what you observed that here the velocity is very less. Velocity is very less, and they are moving mostly in south west direction. So you can see all are moving in southwest direction. Even higher Himalaya is also moving, and higher Himalaya we see this is having more velocity as compared to the south Himalaya. So higher Himalaya is having more velocity, and they are also, the direction is in southwest direction. Then this is the convergence rate. So here you can see the less convergence, and then convergence is increasing, then again it is decreasing here, and then here it is maximum. So this why it is decreasing? Due to the Karakoram fault. So most of this tectonic activity, our this convergence, it is absorbed accommodated by Karakoram fault movement. So it is having dextral fault, and so this fault is basically not allowing too much energy to accumulate at this location. So that's why it is taking more time to accumulate the energy due to this strike slip component. So this is due to this region, we can see the less convergence rate at this patch, and then here it is 18.5 in this region, then here it is 20.2, then here it is 19, then this is again decreasing. So here is a Bhutan, so again one part has been detached, and it is moving with different velocity, and it is having clockwise motion. Actually the whole block is having clockwise motion, so due to that this having different mechanism. So we can see that this coupling is going on. So red part is highly coupled, and these are very potential for this mega thrust earthquake, and these white patches, they are mainly active and they are least coupled. So we can say this is not so potential for any, but these boundaries are very important. So they are where the potential mega thrust earthquake could take place. So that's why we have to prepare for this. And this is the upliftment which is taking place continuously, and you can see that this is the region where we can see the maximum upliftment has been taking place, and this is having lesser rate of in the upliftment. Then this is your depicting the quantifying the slip potential at different location. So you can see it has gone up to 10 meter. So this Bhutan, Arunachal Pradesh, West Bhutan, Sikkim, Pokhara, Kathmandu. So this 7 point, it already has been occurred. So last earthquake occurred in 1934, but it was occurred in this boundary, Nepal and Bihar boundary. But this time this occurred in your Gorkha area. So 7.8. So like that we can expect this earthquake than this 1505 which occurred in long back. So here it has enough potential, 8.7 meter slip potential is there. So we can expect 8.5. Then Almora is expecting 8 magnitude, because there is around 4 meter slip potential is there. Even though there is two earthquake, back-to-back earthquake in 1991 and 1999, 6.8 and 6.7, but you see this amount of slip, this deficit, the energy released is very less as compared to the 1803. So 1803 energy is huge, which was released during this 1803, but if we compare with this earthquake, so this two earthquake energy is very less. And this is the interseismic phase of deformation. So this is the co-seismic 1803. Then again the interseismic phase of deformation is going on, and due to this two earthquake 1991 and 1999, it restricted for some time to mega thrust earthquake to take place. But it will take there will be definitely a megathrust earthquake in near future, because this interseismic phase of deformation is going on, and it has enough potential to release 7.8 and 8 magnitude. And we have also modeled, and we have also found in our data that it is having potential to produce megathrust earthquake. So these are the area 1991 and 1999 earthquake. Then this is our findings. So you can see that this is your representing the dilatation, this color, and this green is representing the vector, maximum principal stress, and so you can see that this compression and extension is very less in Indo-Gangetic Plain and Shivalik region. But what we have found here, that here it is anti-clockwise motion. This Shivalik and in this part of Indo-Gangetic Plain, it is having anti-clockwise motions. So this is and then this unique finding, and this is in this area we have told first time. Then the shearing also it is less compared to your shearing in the part of Lesser Himalaya and Higher Himalaya, and that's why we can see more earthquake occurring in Higher Himalaya and part of Lesser Himalaya in around MCT region, because this is active. And also one more finding is here we have found that this is having a clockwise motion. So this Higher Himalaya is going in clockwise motion moment, and this is going in anti-clockwise motion moment, this part. And also this dilatation and principal strain rate is your high as compared to the Shivalik and Indo-Gangetic Plain. So these are the velocity, and in east component, north component, and this is India fixed velocity with respect to the Euler pole. So this is your India fixed velocity. So as I told you, they are mainly showing this north-south component, and then this movement is in west to south direction, and also this movement is very high, because this part is active and this part is not active. So that's why we can see this, and this is on the Indian plate. So that's why we can see very less magnitude, but we can see some directions only. But here we can see some magnitude, and this one of the stations anomalously showing this different direction. Magnitude is okay, but the direction is different. So due to this this local stress perturbation, our other reason, because this is nearby the MBT, so maybe this local stress perturbation is going on. So due to that, it is showing the different magnitude. But there is no landslide, so we mainly expect this different direction due to this in situ landslide, but there is no landslide, and might be this is due to the local stress perturbations. And this is the regional scale strain rate. So you can see the compression, the pattern of the compression in regionally. So it is having less magnitude, and it is going the maximum magnitudes, and maximum magnitude has been coming 0.07 micrometer per year in Higher Himalaya, here in Badrinath, Ninjar and Himalaya region. So this is before come into the modeling, we have to have some assumption. So this is MHT, where most of the megathrust earthquake take place, and where this is the decollement, and there is no further extension, and all this wedges and thrust systems comes and ends on this surface. And here is the different thrust system, MBT, HFT, and the MCT is divided into MCT1 and MCT2, means Moonsharia thrust and Vakrata thrust. They are lying on this MST. So here we have assumed that deep is around 7 degree, and strike is around 306 degree, width is around 213 degree, 13 kilometer, bottom depth is around 40, top depth is 40 kilometer, and length of the fault is 412 kilometer. So with the help of this, we have gone for the modeling, and this is the model where we give all this parameter, And this is the resistivity model, and this is estimated using this empty data, magnetotelluric data. So you can see this part is almost planar, and this is very brittle, and this is ductile. This is ductile for part, and this is also ductile. So why? Because you can see the fluid here present here, and this and also the present of this microseismicity over here, and this microseismicity, the occurrences of this microseismicity mainly due to this fluid and this ramp structure. So whatever the strain accumulation is going on, this is releasing in the form is microseismicity, and so very conspecially depicting by this, with the help of this crystal structure derived through magnetotelluric data. So this is the modeling result. So you can see the forward normal velocity. So here you can see up to this stations, up to this distance, the velocity is very less. But when you go beyond this distance, so you can see its transition is there, certain transition is there. So velocity is very high in this distance. So this is across the this Himalaya, and starting from MFT. So this is your MFT, and then so you can see that transition is taking place over here, and then you can see the more velocity. So this part is mainly active, so that's why most of this dilatation and area change, it is taking place here. So compression, highly compressive formations, and this is strain component we can see on the surface, and this is the modeling result. So here we have considered the deep angle is deep angle of the MHT is around 10 degree, and what depth this locking depth we found 17.5 kilometer, and this lock depth is around 100 kilometer, and slip rate what we have observed, slip rate is also called the convergence rate, it is 16.5 millimeter per year. So this is occurring over here, but this part is locked, and this is pink tint is showing the coupling, strong coupling is going over here. So, and this all this informations giving an idea that this is very vulnerable in respective of the seismic hazard, and this mega thrust earthquake will take place in near future. Then this is the another case study, this 2015 7.8 magnitude earthquake. So this is the co-seismic information derived through GPS data. So you can see this offset in all the component, north component, east component, and vertical component. So these are the stations. So these are the various stations. So we can say that this co-seismic activity can be captured through GNSS data as well, even though there is a millimeter offset, but we can capture in this as well. And also with the help of this information, we also can conclude that we can go for this real-time kinematic study. So where we can have 15-second latitude, longitude, and vertical information. So with the help of that, we can determine the displacement in real time to see the anomalous activity before an earthquake, and it may help in forecasting the earthquake. And this is the another this study to get the idea about the geodetic deformation with respect to the seasonal hydrological loading. So this is the GRACE data. So you can see in the GRACE data the mass during the pre-monsoon is very less in this region, but during the co-monsoon the mass is very high due to this precipitation and the other phenomena. And then post monsoon we can see the mass has been decreased. So this gives an idea that it must hold and must contribute this in tectonic activity. So this postulate is given by this Patinelli et al. So we also use this postulate for our study to get the idea about this geodetic deformation on our sites in the peninsular sites in your in Indo-Gangetic plain, as well as in the Himalayan sites, and then Tibet sites. So these are the stations which are situated in Peninsula region, and these are in Indo-Gangetic, and your Himalayan region. Then this is Tibet region. So from here we can see that Mandal station is having a higher velocity in pre-monsoon compared to the this post derived north component as well as east component. So we can see that this horizontal component having more velocity in during pre-monsoon than the post-monsoon, and also this vertical you can see in the pre-monsoon it is going down, but in post-monsoon again it is going up. So means vertical upliftment is more in the post-monsoon than in the pre-monsoon. So we can clearly observe in the Mandal data. It is situated in Chamoli region, but this is situated in Shivalik region, Dehradun station. So here we can see there is also some value difference in pre and post, but this is having less compared to your Mandal station. And also we can see that Dehradun is having more vertical movement in post monsoon compared to pre monsoon. So Lucknow is also having means equal. There is no this variation in pre as well as north, pre as well as post in both the component, and also there is a less vertical deflection also in this the time period. But if we compare because this upliftment rate is very high, it is negligible in LCK, but this is upliftment means vertical upliftment is going on. So that's why this is more significant when we study in the Himalayan region as compared to the Indo-Gangetic plain. So then Lhasa also we can see that there this horizontal motion having very least comparison in pre and post, but this vertical is having more in pre, and post is having less. So this Ganga basin and Brahmaputra basin is contributing differently in Lhasa basin. Then this is your peninsular region. So we can see this horizontal movement is also not very significant, but yes, your the vertical movement is significant, and we can see more movement in post monsoon than the pre monsoon. And this correlation is there. So you can see this is the number of earthquake, this is the terrestrial water storage, and your this strain rate is there. So when the strain rate is going down, so it tells that this compression is more, and when the strain rate is going up means extension is more. So this so here also you can see that this hydrological loading is decreasing, so we can expect more compression. So because plate is having normal motion, so this is how the phenomena goes, and then we can expect more earthquake. So here you can see more earthquake, here you can see more earthquake. So number of earthquake will be more during this low hydrological loading than the high hydrological loading. And this is the correlation coefficient between your terrestrial water storage and the different geodetic component, north component, east component, and vertical component. So we can conclude that this Mandal is having more influence due to the hydrological loading than the other stations. So that's why your this graph is coming down, and it is having maximum correlation in Mandal station. So reverse correlation we can see maximum in Mandal stations in this local as well as your Ganga basin hydrological loading. Then with the help of this we can go for this tech study. So these days this is the emerging studies in 21st century and total electron content. So with the help of this we try to study the litho-ion interaction. So before an earthquake there is the seismogenic activity. So rock get over stress. So when it get over stress, so it releases there is a material, pyroxene material is there. So it releases the positive hole. So this positive holes, due to the potential difference, it comes to the surface, and it goes to the atmosphere and it get concentrated outer layer of the ionosphere, and this they deplete, this positive hole deplete the electrons, and because they get diffused, electron get diffused in interaction when they interact with the positive hole, and this deficiency take place. So we can expect this GPS signal will have less time delay, and they will come early to the ground stations as compared to the when the electron density is very high. So then it will take it will take more time to comes to the surface of our your GPS stations. So with the help of this phenomena, we try to see the low tech and upper tech. So there is a formula that so with the help of that formula we get the anomaly. So this is the anomaly map. So this is the upper bound and lower bound. Green is showing the lower bound and blue is showing the upper bound, and red is showing the tech. So wherever we get when the tech goes below the lower bound, we can say that this could be due to the seismogenic activity, and there could be an earthquake. So we can see that simultaneously this is coming at different interval, and when this low tech followed by high tech, then our this postulate it get more confidence, and then we can say that this occurrences of earthquake there is a high chance. So we can see that after that these precursors, when the precursors captured in the stations, so after that the earthquake took place 24 September 6 magnitude. So this is your Mirpur earthquake. So these are the GPS stations, Nurpur, Jia. These are situated nearby Dharamsala. This is Ponta Sahib. This is Masuri stations, and also you can see the this tech variations at different sites. So closer the site, the sites which are very close to the epicenter, so we can expect more disturbance in the tech. So that's why you can see the Nurpur is having more disturbance. That's why less tech we can observe on this time as compared to the other stations and other time. And our window is basically on the daytime. So we do this study and we try to see the precursors on the daytime, during the daytime. And apart from this, you can also see this geomagnetic activity and solar activity, so that when we are studying these precursors, this phenomena should be neutral. It should not be so much that it influence the data, and it affects our understanding. So that's why this parallel study is required when we are doing the litho-ionized interaction. So with the help of this, we can go for this epicenter determination as well. So you can see this is for Nepal earthquake. See this low earthquake, this your low tech.
तो क्या बोलोगे, आपको बोला सर वो तो लेक्चर ले रहे हैं, लेकिन थोड़ा देखेंगे सर जो है सर। ठीक है।
So when we get this low tech, so here we are getting the low tech. So this is coming around 36 kilometer. So the reference point is A. So from here to here, the distance is 36 kilometer. So this is the actual epicenter. So this is you're coming around 28 kilometer. So you can compare that. So, and this is normally we are getting 5 days, 10 days, 15 days before an earthquake. So that's why this method becomes very important for this type of study, and it is giving some idea that we can go for further studies. Means we can decompose this tech data, and so that decomposition means we can separate your solar activity, geometry activity, and this seismogenic activity information from the data, so that we can get more confidence and we can go up to the forecast level. using this method. So with the help of this, you can go for 2D level also. So this is 2D level for mirror earthquake itself. So you can see this epicenter. This is the low tech observed before an earthquake. So this is 16/9/2019, and earthquake occurred on 24 September. So this this method is also important when we are trying to detect the megathrust earthquake. But for low magnitude earthquake, this 2D is not very significant because it is having coarse resolution data. So this coarse resolution is not so significant because it will not spread to the longer distance, because this method depends on the earthquake preparation zone. So there is a formula for that. So this preparation goes within some limit where you can detect this anomaly. So this is another study. This is the same study for Japan, and this type of study you can use it for comparative study of Nepal and your Uttarakhand. This is another study, hydrological loading study, which you can use for Nepal as well. Thank you.